MBA 633 instructional video prepared by Professor Amit Dutta, School of Management, George Mason University. In this clip, we will see how to compute the confidence interval for a population variance. The problem setting is the following. The cholesterol concentration in the yolks of a sample of 18 randomly selected eggs is found to have a mean of 9.38 milligrams per gram of yolk and a standard deviation S of 1.62 milligrams per gram. Construct a 95% confidence interval for the true variance and standard deviation of the cholesterol concentration in egg yolks. So the population of interest here is egg yolks, and the population parameter that I'm trying to estimate is the variance of the cholesterol level in this egg yolk. So what I really want is to get a confidence interval for sigma squared, which is the population variance, and I want to bracket it within a lower limit and an upper limit. So I want an upper limit and a lower limit so that I'm 95% sure that sigma squared lies between these two. That's the usual logic for a confidence interval. So the obvious place to start if I want a confidence interval for sigma squared is the sample variance, which is S squared. Just as we started with X bar, the sample mean, to get a confidence interval for the population mean, and we started with sample proportion P bar to get a confidence interval for the population proportion. Unfortunately, I do not have the sampling distribution of S squared. In order to quantify uncertainty when doing inferencing, the basis for quantifying uncertainty is the sampling distribution of the sample statistic that you use. In past cases, we knew the sampling distribution of X bar, we knew the sampling distribution of P bar, and we could use that to do our inferencing, whether it was confidence interval or hypothesis testing. In this situation, we do not know the sampling distribution of S squared. Rather, I know the sampling distribution of this quantity, n-1 S squared divided by sigma squared, which is represented by the Greek letter chi to the power 2. So I know the distribution of chi squared. I do not know the distribution of S squared. So somehow I have to take that into consideration when doing my inferencing. And the chi-square distribution, a major property of the chi-square distribution that we have to notice is that it's not symmetric. Okay, so it has a bit of a tail to the right hand side, and one of the consequences of it not being symmetric is that we can no longer think of a confidence interval as being a symmetric margin on either side of a middle. Remember how we computed the confidence interval for the population mean or the population proportion? We would take the sample statistic and go equal distances up and down from it using the margin of error. So sample statistic plus or minus the margin of error was our common method of coming up with a confidence interval. But we could do that only because the sampling distribution, whether it's normal or t, was symmetric around the middle. The chi-square distribution isn't symmetric, so I cannot think of building a confidence interval using the same technique as we did for the other two. Nevertheless, I still must come up with an upper limit and the lower limit. The only difference is in this case, I need to compute those two limits independently, separately, not as a symmetric distance around the middle. So let's see how one would go about computing the upper limit. So here is the upper limit, as you can see in the diagram on the right hand side. I've written it by the letter U. I would need to use the chi inverse built-in function, just like we used T inverse and norm S inverse previously for the mean and proportion. Chi inverse. Now this is again one of those nuisances in Excel. For the chi inverse built-in function, the probability that I need to give is the probability to the right of U. This is quite the opposite of what we had to do with the norm inverse function. So the probability to the right of U is 0.025. Why is it 0.025? Because I want my confidence interval to be at the 95% level of confidence. So this area in the middle, I want it to be 95%. So my two tails, I still split the difference, the remainder 5% equally into two tails, just like I had before. The only difference is that these two tails are not symmetric anymore. So U and L are not symmetrically located about some middle. but the two tails are still 2.5%, half of the remainder from 95%. So 2.5% and 17 degrees of freedom, and I get a value of 30.19. So that's what U is. Let's see what L would turn out to be. L is equal to chi inverse of, again, now I have to provide the probability to the right of L. Since I'm trying to locate L, what's the probability to the right of L? It's 0.975. Okay, and 17 degrees of freedom, I get 7.56. Therefore, I have my U is 30.19 and my L would be 7.56. Once I know these two limits, I automatically know that 7.56 is less than or equal to n minus 1 s squared divided by sigma squared is less than or equal to 30.19. Okay, now if you look at these inequality, there are two inequalities here, and the only unknown in this inequality is sigma squared. I know n and I know s squared. So let's see how we can get the upper and lower limit for sigma squared from this. So I look at the two inequalities separately. So sigma squared would be less than or equal to, this is, I'm taking the first inequality, would be equal to 17, which is n minus 1, times s squared, which is 1.62 times 1.62 divided by 7.56. So all I have done, I have taken this inequality, okay, I moved sigma squared over to the left and I moved 7.6 down. Okay, that's all. I've just been flipping around some of the variables and the constants. So sigma squared is less than 5.9, and I think you know what those units are. They are milligrams per gram squared. So let's see, sigma squared would be greater than or equal to this would again be 17 times 1.62 times 1.62 divided by 30.19. Where did all these numbers come from? I just took sigma squared, I moved it over here on the other side of the inequality, took the 30.19 and moved it down back here. So again, flipped around some of the variables and constants to get the value that I need. So this is 1.477. So let me just check the calculation once again. It's 17 degrees of freedom times 1.62 times 1.62. That's the sample variance divided by 30.19. Very well. So now I know that 1.47 is less than or equal to sigma squared is less than or equal to 5.9. So there I have my confidence interval. I'm 95% sure that sigma squared lies between 1.47 and 5.9 milligrams per gram square. I apologize, my machine is so slow. It's an old machine, so when a lot of these programs are working simultaneously, it tends to slow down. There's Excel working, there's the recording software working, so it tends to slow down and not show the screen continuously. It's a bit of an irritation, but that's the way it is. So I'm 95% sure that the variance, the true population variance of the cholesterol concentration in egg yolks ranges between 1.47 and 5.9 milligrams per gram squared. And if I wanted to get the 95% confidence interval for the standard deviation, I would simply take the square root of 1.47, and that would be in milligrams per gram, is less than or equal to sigma, and it would be less than or equal to square root of 5.9, and the units would be milligrams per gram. milligrams per gram. So there you have it, the how to do the confidence interval of the population variance. The logic is pretty much the same as before. The only sort of shift in gears you have to do is that the sampling distribution in this case is not symmetric. It's the chi-squared distribution, so it's asymmetric. You cannot think of the upper limit and the lower limit of the confidence interval as being symmetrically located about a middle. Rather, you compute U and L separately using the chi-inverse built-in function. Once you have the upper and lower limit in terms of the chi-squared values, then you do some reverse engineering like we did over here, using the inequalities. You just take one inequality, take the second inequality, and just rearrange the numbers, and you will get the limit that you're looking for. So the end result of our calculation here is that I'm 95% sure that the variance of cholesterol concentration in egg yolks based on the sample data that I got lies between 1.47 and 5.9 milligrams per gram squared.